Hello, everybody. My name is Mychaela, and I am new to Osmocom development, although I've been doing more general GSM work for much longer. Also, for anybody wondering why there is no video going on with this presentation, it looks like we have established inadvertently a little bit of a tradition in OsmoDevCall, the way anytime the topic of presentation is on voice codecs, it is done in audio mode only, because I remember last time when Niels did a presentation on the issue with SDP description of codecs in Osmo MSC, that was also a presentation done without video. I think he had some different reasons why, but in my case, I'm using Slackware and I never got my webcam to work. I've just been so busy with doing GSM work that don't have spare cycles for debugging. But yeah, it looks like we have an informal tradition in OsmoDevCall, so where if a topic is codecs, then it's done with audio only. And today, we're talking about these three codecs, full rate, half rate, and enhanced full rate. So let's look at what these codecs are. So here we can see I listed them in the order in which they were introduced chronologically. And, we're not covering AMR here, and I'll explain very shortly why I'm not covering AMR while I'm focusing on the basic ones. But, I'm sure to people in Osmocom, this is going to be familiar as far as what they are. But the parts which might not be very obvious is one, people might not realize that only EFR version 1 is mandatory for type approved MS for phones. Everybody else is optional. If you're designing a new GSM phone and want to get it past type approval, you could hypothetically omit other codecs in whatever combination, or omit just the ones you think are worthwhile and omit the ones you think are unimportant, and still be past type approval and be fully compliant as long as you support FR1. And then the other thing that people might not be very aware of is for EFR. If you think about it, the only reason why EFR exists at all is to make voice better compared to plain FR1. There's just no other reason for its existence. It doesn't give you any other benefit. So with this in mind, we get to the fundamental question of, well, why should we even care about this codecs at all, right? So why not work on AMR? AMR is so much better. I remember Vadim was asking me that earlier in some of our exchanges. Why not AMR? So here I kind of explain why not the AMR, because if the purpose of the network, if the whole reason why you're running your own GSM network with Osmocom in the first place is to provide service to vintage mobile phones, especially if you're living in a country where mainstream operator provided GSM services have either already been shut down or are very soon about to be shut down, and you're building the GSM network to be a replacement to provide specifically service to vintage mobile phones. I mean, you have to support FR1 because there could be some really, really, really old phones that just won't support anything else. And then there are just slightly newer phones that support EFR but not AMR. There's a lot of Nokia models, a lot of Ericsson models, Motorola, etc., that, not Calypso though. Calypso does support AMR, but plenty of the earlier ones, like Nokia 5110, 6110, Ericsson IAAA, those kind of, very classic golden era of GSM phones, they all support EFR. And so basically, And so my thinking was, as I was getting into setup of the network, I realized, oh, gee, if EFR is the same thing as the highest mode of AMR, and if I have to support EFR in order to provide, make those, because when they were in the late 90s, when those phones would come out with the more powerful DSPs that can run the EFR codec, that was actually a selling point. They would entice people to buy those phones by saying, look at our model, we support EFR that gives better voice quality. They actually said that in end user marketing. But if the network doesn't support it, then that kind of just nullifies. So wanted to have network support for EFR, and once I'm expending the effort to do network support for EFR, well, maybe AMR can be deprioritized, leave it for later when all the other higher priority work is done. So that's kind of my approach. So as you can see, this is how I run a network currently, pretty self-explanatory. So let's see what some of the first issues we get into as we start supporting these codecs properly on the network side. Yes, DTX is a real issue with all of these, as you can see. And one really important point with DTX with these older non-AMR codecs is you have to think of it separately in downlink versus uplink. So if you want to enable DTXD, meaning discontinuous transmission and downlink, you have to have a multi-carrier cell. So you have a multi-TRX. I guess it's really not so much the TRX as how many frequencies you have, how much spectrum you have allocated to your cell. So if you have a cell with more than just your BCCH carrier, with more than just T0, then you can enable DTXD to where you physically turn off TX power during times when there is no speech. But if you only have a single carrier cell, if you're operating in a teensy sliver of a guard band around LTE, and you don't have a whole ton of spectrum, you just run a single ARFCN cell, you're not allowed to physically switch off TX. You can do like a fake DTXD, which we'll get to, is what I've implemented recently in OsmoDevCall. But as far as physical DTXD, where you actually turn off TX, that's not possible when you have just a single carrier cell. On the other hand, in the uplink direction, you can and almost always want to do physical DTXU. So in the uplink direction, you just set it in your Osmo BSC config. You say DTX uplink, you enable it or disable it. And if you disable it, you'll just be wasting battery power in phones because the phone will have to burn up its battery, transmitting the burst in every single frame, whether you're speaking or not. But if you do DTX uplink enable in Osmo BSC config, then the phones can just not transmit anything, not turn on their transmitter during times when the speaker is silent, and so you're saving battery. And then, of course, there are interference concerns, but primarily saving battery. So, as I said here, high quality retro networking operation, you kind of want to support a combination of DTXU, but not DTXD. And so, okay, now we say, all right, we want to enable DTXU. Well, the moment we enable DTXU, now all of our Osmocom network elements that are in the path have to understand what a SID frame is. They have to correctly, gracefully handle SID frames, which is a specially modified codec frame. And here is the really important part is, I'll get to that in more detail later, but your classic libGSM, which almost everybody, including me, in the FOSS community use for decoding GSM 06.10 codec, does not support SID. And what's really important is that if you look at the structure of a SID frame, it's a modified codec frame, yes, but it's modified in such a way to where you have to recognize it as SID. If you take a SID frame and pass it to a non-SID aware decoder, if you try to decode it as if it was just speech, you'll get garbage. It wasn't designed to work like that. It was designed to be recognized. So that's first little detail here. And so what you see on this slide here, this, if I'm not mistaken, was the beginning of my Gerrit, or Jared, how you pronounce it, patch contributions this past season, where I started improving the SID detector in libOsmo core or libOsmo codec component of it. So, because you have to have this third state of invalid SID. I assume, it was obviously years before I joined the project. Whoever originally wrote the functions like Osmo FR, what is it called, that checks if it's a SID or not. It was just a binary result. It was a Boolean result, right? It is a SID or it is not a SID, which, at first glance, it seems like, yeah, you just check for that magic code word and it tells you is it a SID or is it not a SID. But you also have to have this third state because, as I explained, if you don't have that third state, imagine what will happen is if you transmit a SID on a radio link and random bit error, something happens, the SID arrives corrupted. You got a corrupted SID on the receiver, and if it misses the check, if you say, this is not a SID, this is a regular speech, you try to decode it as regular speech, you get garbage, because SID was never meant to be decoded as regular speech. But at the same time, if it's badly corrupted, it's not really a valid SID, so you have to have it this third state. And here I explain about the thresholds. That should be, self-explanatory. Engineering trade-offs is, any kind of threshold. Like here's the for FR and EFR, the spec actually says this is what your threshold is. Whereas for HR, which I'll get to, we have to come up with our own. But at least, whether the threshold is prescribed by the spec like it is for FR and EFR, or whether it's something that we as Osmocom would have to come up with on our own if we decide to go down that path. In the case of HR, either way, it is a compromise. There will always be some times where a speech will get misinterpreted as invalid SID, and the frame will get dropped, or sometimes vice versa in really unusual conditions. You might get a SID corrupted so badly to where it misses a check. But the idea is to tune your threshold so that these unfortunate events will be as rare as possible. That's engineering trade-offs and compromises. And so, more explanation on exactly what it means for a SID to be classified as valid or invalid. So today we have functions in libOsmo coding, libOsmo codec. We have functions there that for FR and EFR will do a ternary classification. You give them a frame in RTP encoding, and it will tell you, is it speech, is it valid SID, or is it invalid SID? But what do you actually do with the result of that classification per the spec? What is it supposed to tell you? So here on this slide, I explain what that classification does. So if it's classified as valid, then the ultimate decoder on the end will extract comfort noise parameters out of the frame. But if it's classified as invalid, it says, the frame is too corrupted. You can't get any CN params out of it. But still initiate or continue CN generation. And that's important because if it was just your regular BFI, let's say you got speech, and bam, you have a BFI, completely corrupted frame, right? In that case, the decoder will invoke the ECU. It will invoke the error concealment unit that will try to act as if it was just a lost speech frame and try to hide the error from the listener. But if it was invalid SID as opposed to regular BFI, Then RX DTX handler knows, instead of invoking the ECU, I'm going to invoke the comfort noise generator instead, using old CN parameters, which it already has from previously. So that's what this ultimately happens when you do an embedded classification. And again, once again, trace often compromises like in all of engineering. For FR and EFR, the spec says if you got a 1-bit error, you're going to still count as a valid SID. If you got 2 or more bit errors, that's invalid. So for FR, EFR, they tell us. For HR, they don't. So, but this is just, where we're headed with this. So now we get to the painful codec, the half rate. So, which I originally wasn't even focusing on. My original plans for this were to just focus on FR and EFR. But when I saw that in the Osmocom community, the HR codec seems to be receiving some significant attention with the other issue that was going on with the two formats for it. Okay, well, if the community cares about half rate codec, I better study up on it and see what the situation is. And so one of the first difficulties that we have with half rate is that, well, first of all, in original architecture, they envisioned the SID detector as being closely coupled to the channel decoder. And if you think about it, that you're trying to detect how many bits are in error. In the case of HR codec, when you do the GSM 503 decoding, there is this reordering step. I guess there's bit reordering in all of the codecs, but in HR, the difference is based on the voiced versus unvoiced decision. It will use one reordering table or a different reordering table. And that reordering happens logically within the 0503 decoder block. So when you're looking at the 14-byte, was it TS108-318 output from the 0503 decoder, by that point, the decision has already been made. Is it voiced or unvoiced? And it reordered the bits one way or the other. And the 2 bits that indicate the mode, they're part of the SID field. So they're going to be set to 1 in a correct, uncorrupted SID frame. But now imagine if those 2 bits just happen to get corrupted. And now suddenly your invalid SID, it will appear to be an unvoiced speech. And if the SID detector completely misses it, then the unvoiced speech, a bogon at that point, will go straight through to the decoder, and the decoder will produce unpleasant noises. So in our original architecture, the idea was that the bit counting rules with thresholds of how many bits you need to be in error in order for it to be considered valid versus invalid versus speech. The idea was that this bit counting magic will be done inside the 503 channel decoder. So in our case, it would be in Osmo BTS TRX in lib Osmo coding, not codec, where we would have to do this bit counting before we do the reordering. So here I was saying, this part right here, this right here is an if statement. So we're going to address this if statement, later in the discussion part. But if we want to, as a community, go down this path, we will have to add this function to the GSM 503 decoding function in libosmo coding. And okay, implementing the function is the easy part. I can easily implement the function. The hard part will be coming up with our own thresholds, because we don't have a spec telling us this is where the threshold is going to be. They leave it up to the discretion of BTS manufacturers. But of course, the fundamental theory stays the same. You have to pick the threshold in such a way as to minimize the chances of the check being missed and giving you the wrong result. And they do give this non-normative example in that infamous 0606 C code. But, again, if you decide to go down a path, one of the things you're going to see with this mystery BCI flag. So in the finished spec, they have a BFI flag for bad frame indication, and they have a UFI flag for unreliable frame indication. And those I explained in the specs. I'll cover them here in later slides. But what is this BCI flag? It's nowhere in the spec. I don't know what it stands for. Maybe all I can guess it was some kind of leftover from an earlier draft of the design that never made it into the final spec or something. But yeah, that's just. So even if we were to use that non-normative example and try to use that as our reference for the thresholds, it's not as obvious. So that's the problem with the half rate. So let's see where we're headed with this. All right. With the standard decoders. So when you have any of those codecs, full rate, half rate, enhanced full rate, what actually happens on the receiving end of the frame stream? Your standard spec prescribed decoder. Also, Vadim was asking maybe just a typo about the BCI flag, I assume. No, the answer, let me go back to that slide. So I assume that Vadim was saying maybe just a typo in reference to this flag. No, I'm very certain it is not a typo. If we as a community decide that we do wish to invest more effort in HR1 codec, which will be a discussion in itself, but if we choose to go down that path and we actually want to study it in more depth, I'll show you the code, and it's not a typo. There's a whole separate little stanza in the code that deals with this this mystery thing that was dropped apparently from the final published draft of the spec. So anyway, back to what I was saying about the decoder. So this part, the part that you see on this slide right here, this part is actually common on both the network side and on the phone side, mobile station, exactly the same. I mean, here we are concerned with the network side, of course, but just want to point it out. So, and this is the part, like I was saying here in the last paragraph, it was so non-obvious. This was non-obvious to me. I had made mistakes in this area when the first time I ventured in this topic back in 2016 in the context of Freacalypso, I made some of the exact same mistakes that I see being made on the network side. So I can only expect that everybody else is going to make the same mistake if don't fully study it. So it seems like to a naive person like I was when I approached this for the first time, you just take the output of the 0503 channel decoder, network side, mobile side, either way, and you just feed it into a standard decoder for the speech. So in the free software community, we have libgsm, which was not written by anyone in this room for sure. That was, dates from the early 90s, I think. And apparently the two people who wrote it are still around. Maybe they even provide a little bit of email support or something, but it's definitely very, very old, very mature piece of free software. That libgsm is a passing spec compliant implementation of 06.10 encoder and 06.10 decoder. And it's very easy to test it for correctness because you have, we all have the official test sequences published by ETSI. Back in the days when libgsm was written, apparently you had to pay money to get those test sequences, but these days you just download it from ETSI in a zip file, and I've tested it. Anybody here is welcome to test it. It's easy to confirm that the libgsm included in lots of Linux distros and whatnot already it is a truly correct implementation of a 6.10 encoder and decoder. But there is this little but there, is that what's missing is the RxDTX handler. So in the standard architecture, you have the RxDTX handler sitting in between the 503 channel decoder output and the input to the speech decoder proper. And it's especially so for the FR1 codec, because for the FR1 codec, this RxDTX handler is a modular piece. It's a separate modular component. And what I found so strange is when I first figured all of this out a few months ago, I think it was like October or November last year when I figured all of this stuff out. I searched high and low amongst the existing body of free software, and I was unable to find an existing implementation of FR1 RxDTX handler. So I had to write it myself. So that's what Themyscira libgsm FRP is. And the new version of ECU that has recently been merged into libosmo codec is based on that. It's just a stripped down version. But I just find it strange that there were no pre-existing free software implementations. It wasn't even all that complicated. Just had to read the specs and implement them. But still, whereas for HR and EFR, for the other two codecs, it was built into the speech decoder from the get-go. From day one, you'd get the official reference C source from ETSI for half rate or enhanced full rate, and the RxDTX handler is already there. It's inseparable. It's impossible to create an HR or EFR speech decoder without RxDTX handler. It will always be there. But for FR1, separate modular piece. So just something that we all need to be aware of. Yes, what Harold's comment, I guess this relates to historical development. Likely FR was specified without DTX, and then later it was added in between for the other. Yeah, most likely correct. Obviously, I wasn't there when all this happened. All this happened long before I entered the scene. But Harold's guess is most likely correct. Yes, that's probably why. Why it is a modular piece for FR1. But in any case, as developers of Osmocom network side software, we have to be aware. We have to know what the standard decoder architecture is so we can plan our work around it. So let's see where we're headed now. So, all right. Now we come to this very interesting topic of transport within RAM. And this part's really important. This is where the network side is kind of more interesting than the mobile side, because here we have these interfaces and components. On the mobile side, it's all in one box, but here you have these interfaces. And as you know, most people in Osmocom probably know, a lot of specs like ABIS were only defined for T1E1 transport. There is no official 3GPP spec for ABIS over IP. So, and when you look at your spec of a T1E1, the way they envisioned the GSM codec frames being transported, you have all of these out-of-band flags, which are not present in the RTP version. So what are these out-of-band flags? They accompany every speech frame. So every 20 milliseconds on the ABS interface, you have the frame being transferred in the uplink direction from the BTS to the TRAO. But alongside with the frame bits, you have all these out-of-band flags. So you have the BFI, and here I explain what they are. And the TAF is it's a DTX-ism, that the way DTX is defined in both uplink and downlink for in the classic codecs is it's tied to the SACH multi-frame. So you have this alignment marker that tells you, is this frame aligned with the multi-frame or not? Because the RxDTX handler by the spec cares about this flag and uses it as part of his decision logic. And then we also have the SID classification. So this is actually a 2-bit ternary flag that classifies is this a valid SID, is this invalid SID, or is this a non-SID speech? And for FR and EFR, the out-of-band flag is redundant because the recipient can simply look at the payload bits and apply the prescribed rules and reconstruct the classification, which is what we already have the function in libosmo codec, the functions I added back in March or so, that do this classification. But for the half-rate codec, you can't do this, because for the half-rate codec, only the BTS can make the classification, because there is no single set once and for all rule. But so in architecture, they have this SID flag out of band. And then they have this little weird flag called UFI, which is only for half-rate. So with half rate, the idea of a UFI flag, and of course there is no guidance given. They never tell you as to exactly when, under what conditions the BTS should set that flag. It's just there. But it basically says that if the channel decoder believes that the frame is suspect, so it's not outright bad, should probably be decoded as good speech, but just be careful with it. That's what the UFI flag says. And what the standard decoder, and that part is in the specs, in the 06.06 source code for the half-rate decoder, the RxDTX handler will look at the UFI flag, and like if you have a BFI flag set, if it's a bad frame, then it just invokes the ECU function. It does error concealment. If the UFI flag is set, it will try to decode the speech, but it will watch the signal level, and if the signal level gets too high, it'll be like too loud of a pop on the audio output, and it says, this is unsafe, and it mutes that frame. So that's the function of the UFI flag, and that's, like I said, it's another out-of-band flag for half rate. And these are the specs, so you have one spec for 08.60 for FR and EFR, and 08.61 for HR. These are the specs for ABIS over E1. So that's your classic transport. So, and now the other really big thing we have to cover is TFO and TRFO, because what you see on this slide, that's at the heart basically of what happens when Alice is talking to Bob, and both Alice and Bob are GSM users. So, if Alice is calling her bank, or if Bob is calling his insurance company, and they're just, your regular office lines out on the public switch telephone network, then of course this can only be a transcoded call. So in those cases, you have just one GSM leg, you have the outside world, which is G.711, and you have a single network side transcoder in between. Everything's simple and straightforward. But what if both Alice and Bob are GSM users? What then? So you want to avoid the tandem transcoding. It'd be very wasteful and degrading speech quality if you were to say, if Alice is on the phone, her handset encodes her speech, then the network, let's say, were to decode Alice's speech, then pass it to another network element, have that network element re-encode it for Bob's call leg, and then have Bob's handset decoded in the end. Well, now you have basically two lossy codecs running in tandem, which degrades speech quality and wastes DSP power and all that. And so you have two different solutions. You have TFO and TRFO. So TFO is what would happen in the original classic architecture, where you would have the transcoder. When the transcoder it was physically implemented as a TRAU, the transcoder rate adapter unit. what would happen is every individual call leg would always pass through the trough, and the trough would basically convert every GSM call into a G.711 64 kilobits per second call. So even if, in a classic architecture, even if Alice and Bob were both customers of the same GSM operator, they could be in the same town, they could perhaps even be served by the same BTS. The call from Alice to Bob would still pass through a trough on each leg of the call, and then in the core network it would be switched, presumably by the MSC, at the 64 kilobits per second level. And so in that environment, the way they would avoid the undesirable tandem situation is by doing in-band TFO. So there was an in-band signaling protocol. The G.711 interface to the trough, it's all normal G.711, but they steal 1 bit every 16th sample during the initial setup phase to exchange in-band messages between troughs. And if they figure out that both troughs use the same codec, then they put it in a special pass-through mode where they steal the 2 least significant bits of every G.711 PCM sample, and they just pass the codec frames right through in that manner. But the end result is now you have codec legs from Alice's phone going to Bob's phone without a double transcoding in the network. Whereas in newer systems, like in Osmocom self-contained network, we have TRFO. So instead of tandem free, we are transcoder free. So transcoder free means we don't even have a transcoder in the first place. So pure Osmocom without the Mosquito wireless extensions does not have a built-in speech transcoder. So when you run an isolated self-contained internal MNCC Osmocom network, then every call will be a TRFO call. But again, the end result is exactly the same. You're still taking codec frames from leg A uplink and pass them to leg B downlink. And so the questions stay the same. All the questions raised in this first paragraph are exactly the same whether you are doing old-fashioned TFO or modern TRFO. The problem stays the same. So what if you have uplink? What if you have DTX on the uplink, but no DTX on the downlink? And even aside from DTX, what if you just got some BFI? You just lost some frames for whatever reason. It could be radio link errors on link A. It could be fetch stealing on link A. It could be packet loss in the IP network in between. For whatever reason, if you have a frame gap in the downlink stream, because the reason why it matters is, going back one slide, in your classic architecture, in your traditional Yvonne style ABIS, on the uplink, you have all these out-of-band flags, but on the downlink, they expect a perfect, pristine frame of speech frame of the speech frame of the speech frame without any aberrations. So how do you reconcile those two? So reconciling between those two is what we have to do in the case of both TFO and TRFO. And this is the spec right here. This spec is where I found the rules being set for what should be done in these types of scenarios. And like I say, basically, it's an ECU plus a comfort noise generator operating at the codec frame level, at the level of speech parameters. So, but the fun doesn't stop, because the unpleasant part is right here in the first 2 paragraphs. So they tell you it shall be done like this. Because as you know, probably 3GPP specs don't use the word must. They use the word shall. And so they say this type of component shall do this. And so the spec says, you shall do this, but no algorithmic guidance. They just say subject of manufacturer dependent. Oh my God, it's like, what are we supposed to actually do? So here, we'll discuss this part when we get to, to the discussion phase. I would love to see what the real trials actually do. It's just my curiosity is getting to me. How do they actually implement those horribly difficult rules? And here I thought about, okay, like if I had to implement these rules, how would I do it? For FR1, easy. Basically, take, the ECU that has recently been merged into libosmo codec would be almost sufficient. Almost not completely because that was just the ECU. But if you were to take the complete Themyscira libGSM FRP, which is the full RxTTX handler for FR1, consisting of ECU plus the comfort noise generator and the control logic that ties them together. Just take that whole piece and that will satisfy the rules of C3211. So easy for FR1. For half rate, I looked at the reference code for 6.10 and their built-in ECU and comfort noise generator is somewhat modular. It's not as modular as it was in classic FR1, but it's kind of somewhat modular to where it might be possible to factor it out with some work. But for EFR, oh my God, for the EFR, it's such a difficult task. Because for EFR, there is no modularity. For FR1, you look at the reference decoder from ETSI, and all of the logic for the ECU function, and all of the logic for the comfort noise generator function, all those logics are interwoven throughout the body of the decoder, digging deep into the decoder. It's not just the front end anymore. And so if I had to implement a modular piece that takes an EFR frame stream in and puts an EFR frame stream out and applies ECU and comfort noise generator transforms to the stream, I don't know how to approach this. It's like a really off-puttingly difficult problem. And on top of it, not only is the problem of putting it difficult, but the whole point of EFR is to give better voice quality. And so what if we were to come up with some quick and dirty implementation that kind of sort of does the job? What if we ruin the voice quality improvements by doing so? So all of this thinking brings us to the next slide. So this is what has actually been done. So what you see on this slide in front of you, this has already been merged into OsmoBTS master. So that has been my kind of main focus of OsmoBTS patches over the past couple of months. So what I did here, it's basically kind of like a cheating. So what we are doing right now in OsmoBTS does not fulfill the letter of the spec, but it achieves the desired result. And if I dare say, the result is actually better than what we would get if we tried to do the spec by the ladder. Because the idea that I took here was, what if we can just fool the GSMMS? Because obviously the GSMMS on each end has a fully spec compliant RxTTX handler. And for them it's easy because the people who wrote, who did the firmware for the DSP on AMS, they just took the code from ETSI. I don't know if they had to pay any patent licenses or whatever, but even if they did, they obviously took care of it. So the standard, reference EFR, and HR1 and FR1 decoders and standard spec compliant or XTTX handlers, they exist inside every GSMMS. That's a known, obviously. So what can we do on the network side to fool the MS into behaving the way we want, into producing the output that we would like? So that's exactly what I did in the OsmoBTS series of patches. So, breaking it down one by one. So if we have if call leg A had DTXU, which most of the time it will, but we don't have physical DTXD, well, because one, OsmoBTS TRX does not even have physical DTXD at all. OsmoBTS only has it for AMR, and if you don't have enough spectrum, the point is moot anyway. So can we do logical DTXD without physical DTXD? And yes, we can. And the result is, again, for the RxDTX handler and AMS, what they see is the same as what would happen if that call was done in the classic network. That's the result. The same thing happens with the bad frame gaps. You know, we could try doing the ECU in the TRFO path in the network side software, or we could just transmit inverted CRC3 and let the RxDTX handler handle it. Obviously, the second option is easier because it's less work for us. It's the same for all three of these codecs. So if you look at all the patches that have been merged into OsmoBTS, there is very little distinction between FR versus HR versus EFR. They all three handle the same. And I would say, what's the end result? For FR1 and HR1, I would say the end result we get with our current OsmoBTS approach is probably same quality as what we would have if we did exactly by the letter what the spec says. But for EFR, I'm sure we get better result by doing what we did compared to the official way. Because again, I don't know how to do the official way without butchering the quality. So that's OsmoBTS TRFO path. Let's see. So now we get to RTP encoding. That's, yeah. So here you can see the history of how the RTP payload formats came about. So, with FR1, it's very obvious that there was no consideration of GSM RAN. This was done, all the work for the RTP payload format standardizing for FR1 codec. When was that? I think it was still late 90s at that time. So we're talking a full decade before Osmocom, full decade before anyone could conceive in their wildest dreams of using free software to implement a GSM network. Back that may have been even before the ciphers, before A51 and etc. Before all of those were fully published, allowing open source implementations, etc. So there was just no consideration of open source IP-based GSM RAN, and the people were just thinking of taking the GSM 06.10 codec and repurposing it for applications that have nothing whatsoever to do with GSM. And so that's how they came up with the RTP payload formats. Then I don't know what was this Typhon group in Etsy, but obviously it was not the group Spécial Mobile. I'm sorry, my French is very rusty. So they just very obviously copied FR1. And so all of the metadata bits were dropped. So when you look at GSM 08.60 or 08.61, as I was covering previously, we have all of these out-of-band metadata bits that accompany, and yeah, I hired the Typhon Telecommunications, the Internet Protocol Harmonization over Networks. I know what it stands for because it's on the title page of the TS 101 318 spec. On the title page, it does this decoding the abbreviation. But as far as politically where the group stood and how, if they related at all to Group Spécial Mobile or not, that I'm not privy to. And looking at the product of their work and looking at what they actually produced in the spec, it does not look friendly at all to GSM RAN implementers. And again, the big problem is they dropped all those out-of-band metadata flags. They just kept the codec. And so here I say, okay, well, what do you have to indicate BFI? How do you indicate BFI? So looking experimentally at IP access nano BTS with and again, thanks to Harald for doing the testing because I could never get it to work on my end. But yeah, Carl's comments was that it's about GSM speech codecs with H323. So yeah, I'm not really familiar with H323, so I'm not qualified to comment on where it fits into the picture. But on the subject, here Carol says it's the ITU Etsy alternative to SIP that was used by NetMeeting. All right. Well, okay. Well, that's what it is. But still, the point remains that for IP-based GSM RAN, it's not very good. So, looking at IP access nano BTS, if there is a BFI condition in the uplink, what happens? Well, they just send nothing at all. They just create an intentional gap in RTP stream. And this was also Osmo BTS behavior up until very recently. So just within the past couple of months, when I joined the project, we introduced this option, RTP continuous streaming VTY option there, which basically gives you the option of sending zero length RTP payload. But still, the zero length RTP payload, it's only a timing tick. It gives a timing marker so that if the RTP stream receiver uses the stream as a timing source, you don't get a timing discontinuity. But there is still no data bits. You still have a complete omission of a frame. That means BFI. And also, this was very recently fixed. I think it was Redmine ticket OS 6033, if I'm not mistaken. But this bug was fixed very, very recently in Osmo BTS TRX. Apparently, some years ago, someone somewhere got the idea that they could indicate BFI by sending all bits of payload to zero. Well, I'm sorry, no, that is not BFI. In the classic architecture, BFI was an out-of-band flag. Therefore, there is no possible in-band pattern that can indicate BFI. And if you feed this all zeros payload to a standard spec-compliant RxDTX handler, it will not interpret it as a BFI. It will be a bogon. It will produce bogus decoding. So, but back to the topic of RTP encoding. So on this slide, I show why this is a problem. So in other words, these IETF Typhon standardized RTP payload formats for FR, EFR codecs. Well, what's so bad about it, you may say, right? Well, okay, they dropped those old obsolete out-of-band flags. They made it simple and easier for non-GSM people to understand what's so bad about it, right? Might be the naive reaction, but these problems here that I pointed out, these are actual functional regressions from classic GSM 08.60 to RTP. And in particular, I draw your attention to this line here, to this little SKR diagram of, again, what if. Yeah, so what started all of this work, what was the trigger for me to get, involved and contributing to Osmocom and improving all these things I'm talking about, was because I was building a GSM network that interfaces to the outside world in G.711. So I needed to implement a transcoder, network edge transcoder specifically, and I wanted to make my network edge transcoder behave as closely as possible to a traditional TRAO and to replicate this retro networking GSM experience. And one of the things I'm still on my wish list, hasn't done yet, is to implement TFO. I already covered TFO earlier, so you know what it is. So TFO is this in-band protocol that exists inside a G.711 PCMU or PCMA sample stream. So I definitely want to implement the protocol someday, hopefully someday soon. But the TFO frames, once you've done the in-band signaling successfully, once you've negotiated, yes, that the transcoders on both sides use the same codecs, and they agree per the in-band protocol to enable TFO, once the enable switch is thrown, you will start getting these TFO frames being emitted. And a TFO frame is just a very slightly modified TRAO UL frame. So it's a frame straight from GSM 08.60 spec for the uplink direction, just a few bits modified here and there, but all the semantics are still the same, and all the really important out-of-band flags are there. And so, the truth is, like when I say no ability to indicate BFI along the data bits, You may wonder, why do you care about data bits? If you know that this is a bad frame, why do you care about the presumed bad data bits? Well, one, in the original E1 ABIS architecture, they're always there. So in this diagram, if we imagine if we've originally started with E1 ABIS, they're just dropping bits here, we're just losing data. And two, the classic the official decoders from ETSI for both HR and EFR, they both, under some circumstances, make use of some bits out of a damaged frame. So even if you have a frame with BFI flag being set, the way the decoder knows this frame is bad. If you decode it straight through without any special treatment, you're going to get really horrible noises on the output. But nonetheless, they still do partial decoding. They don't throw the frame altogether. There are some bits from the error frame being retained. The logic is implemented in such a way to where it can be too loud of a pop. So, and I'm not the person who designed that. My knowledge of codec theory is not to the point where I can make an independent judgment call on whether it's a good or bad design, but that's how it is in a standard decoder. And so having a transport format artificially block the ability to pass the bad frame bits along with BFI is just bad. And then, of course, losing the TAF bit, which is based on the frame number. So, in a BTS, like Osmo BTS, to derive a TAF bit, you just look at the frame number. Whereas in this flow from E1 ABIS to Osmo MGW, you'll be looking at the TAF bit that comes from the E1 ABIS. But either way, that flag is there. In RTP, it's just lost. And here, again, I would like to just pass the whole Trauer UL frames out. So basically, in this network edge transcoder, I will be putting out TFO, but also there is the built-in decoder function of the transcoder itself using based on traditional Etsy libraries where all these bits matter. So this is my solution here on the slide. So this is the part that might raise some eyebrows in the community, but I don't know of a better way. Because as far as I know, nobody in the Osmocom community has ever tried writing their own 3GPP style specs, putting on the hat of a 3GPP spec author. But that's kind of what I did here. So I wrote my own spec. It's called Themyscira Wireless Technical Specification TW-TS-001. And the link to the spec was posted earlier on the OpenBSC mailing list. So I'm sure those of you who are curious about this news may have probably already seen it. So the spec is hosted under my domain name. It's going to stay there. So it's a spec that I wrote in the style language of 3GPP specs. And, the title of the spec is Enhanced RTP Transport for FR and EFR codec frames in IP-based GSM RAN. Here in the slide, I explain what it is. Very similarly to how RFC 5993 for half-rate codec, how they prepended one more header byte in front of the payload to give the seed classification. I'm actually have done a similar thing here, but for a different purpose. I'll cover the RFC 5993 later, and as you'll see, it doesn't do the same thing as what I'm doing here in TWTS01. But in this spec, again, you're more than welcome to read the actual language of the spec, written 3GPP style, as it covers why and how and the format of the flags. And I have a proposed implementation for Osmo BTS. So there's a feature branch, and there's just 2 patches on that branch. So first patch, accept the format, and second patch VTY option to emit this format. So right now it's on the feature branch. I would be quite happy to push them to get it for review, but I wanted to kind of feel the community's, gauge community's feelings first before I just spring on everybody, so maybe we can cover this in the discussion part afterwards. So that just describes what it is. Now, all right, so what about the half rate codec? So that spec, which, I just presented, TWTS01, it's just for FR, EFR. That one does not deal with half rate at all. But when we look at half rate, RFC 5993, it really doesn't solve anything. So the problems which were there in the traditional IETF, Typhon, RTP payload formats, those problems are still there, even in RFC 5993. As you can see here, they are summarized in these bullet points. I don't need to read, it's obvious. So all the same problems are still there. And here let's say that I do not currently use this codec, so I don't really have my own horse in this race when it comes to half rate. But, from the perspective of, being a community member, contributor, for other people who do care about half rate, this is just a proposal here. So basically what you see, the second half of this slide, that's only a proposal, may or may not happen depending on the community interest. So you could create a spec that basically extends RFC 5993 with similar functionality to what I did in TWTS01. But as far as, again, as far as the actual format goes, I was saying that unless we do this extension, this was the part that I was a little bit mistaken about earlier. So when I was implementing the patches for Osmo BTS, that did the harmonization between TS 101.318 and RFC 5993 to where both formats are now acceptable to every Osmo BTS model, and also every Osmo BTS model has a VTY flag to select which ones you're going to transmit. At the time when I did those patches, I had the mindset that we should be adopting RFC 5993 as a forward-looking external format because of the extra header. But thinking about it in more detail, that extra header, the way it is defined in RFC as it stands, the unchangeable word of RFC 5993 as it stands, does not give us any more functionality versus plain TS 101.318. Because look at it here. So missing frame, but we can just send a zero length payload, achieve the same effect. The seed classification, yeah, but you can't do invalid seed. And here's the other thing is, let's say we implement the seed decoder, seed detector, let's say we come up with our own thresholds for how many bit errors counts as valid seed versus invalid seed, and where there was one threshold between valid seed and invalid seed, and another threshold between invalid seed and non-seed speech. Let's say we implement these thresholds, we put it all in there into our Osmo BTS TRX as part of the 503 decoder. And then what? How are we going to actually communicate this result in RTP? If we have to obey the rules of, if we are not allowed to invent our own RTP payload formats other than a non-default VTY option, if we're just sticking to standard RFC 5993, we really can't do anything different from what we can already do in TS 101.318. So basically what I'm saying is my end summary is it doesn't help GSM RAN implementers, unfortunately. So again, point to be discussed later. And so now the other topic that is still unresolved is the bogus ECU call. Let me take a sip of my juice. So, as I've been arguing for a while, the invocation of the ECU in the uplink path of Osmo BTS TRX is a bogon. It should be considered a bug. So, as I'm saying here, is in the traditional architecture, there's just never a clause for any BTS to apply an ECU in its uplink path. If you've got an error from the radio side, if you've got a if you receive nothing at all on the radio, if you never, like if you get the knobs in the TRX implementation to you never even picked up the training sequence, or if you got garbage on the air that completely fails off IO3 decoding, or if you got fetch instead of speech, then basically that's a BFI condition. Yeah, BTS is not supposed to do ECU in this condition. It's supposed to just mark this is a bad frame and let the downstream figure out what to do with it later. And say, okay, well, what about TRFO, right? If this is, if call leg A is going to call leg B, then the spec does kind of call for an ECU in the path here, but one, it doesn't say it's going to be an uplink, and originally it was in a tau, but we can't do it for EFR. For EFR, too difficult. If we already have what I covered earlier in a slide about TRFO, what we currently do in Osmo BTS, all models in the common layer for call leg A going to call leg B, we already have a better handler that's without an ECU, without a comfort noise generator, just by emitting synthetic BFIs, by emitting the inverted CRC3, we basically trick the spec compliant RxDTX handler in the mobile station into doing all of the heavy work. So basically the end result is there should not be an ECU call anywhere at all in Osmo BTS, just not at all. So, but of course, what I've heard previously, I put this slide in there because probably many people in the community might be familiar with the existing misconceptions. So some months ago, when I first raised the question, why is this ECU there? And why is it only in Osmo BTS TRX version, not in any of the others? I was given the story that supposedly the proprietary PHYs have the built-in ECU somewhere in a DSP black box, and that they had to replicate that logic in Osmo BTS TRX. Well, a simple experiment shows that's just not the case. It's very easy to do an experiment, at least with the TXU. I mean, it would be more difficult to simulate this condition outside of the TXU, like say if you're in the middle of a speech and you just create artificially bad radio conditions with some kind of channel noise simulator. I don't have fancy equipment like that. But what we can tell very easy through experiments. One, it's very easy to create fetch activity. You can just press some DTMF buttons during a call because DTMF is signaled over fetch. When you induce fetch activity on the uplink, you can see what the Osmo BTS PHY puts out, and you can see that it does not put out anything on TCH at all. It only puts out an L1, I don't know, I could be wrong with terminology, but whatever is the right terminology for the packet message primitive, whatever it's called, exchange between the ARM layer and the proprietary DSP, whatever thing that the DSP PHY sends out is fetch specific. It delivers a fetch frame when a fetch was received, does not deliver anything at all on the TCH side, so obviously no ECU output. And when you have a DTXU pause, and so the MS has its transmitter turned off, and the PHY is in the BTS is decoding radio noise, most of the time you get zero length payloads. But every now and then, look at this paragraph right here. There's just basically zero length payload, bogon. Zero length payload, bogon. These occasional interspersed bogons, I'm pretty sure that's the result of the CRC3 check, which has a 1/8 probability of saying good when decoding random noise. So that's just further proof again that there is no ECU in the DSP. I'm sure of it. Now, okay, so how did people come up with this mistaken belief? What was it that made early Osmo BTS TRX developers all those years ago? What made them think that they needed to do the ECU? Well, this is my analysis. The result was a bogon. How a couple slides ago I showed that in the case of a BFI, they would send a packet of 260 bits of all zeros as FR1 payload. Well, that's a bogon. And so if that bogon was going to the receiver on the other end, they would certainly get unpleasant audio, or at least maybe not totally unpleasant, but certainly worse in comparison to what you would get with a System BTS, where they get a proper BFI. And so that led them to the mistaken belief that they need to do the ECU. And then when they did implement the ECU, they masked the bug. So the bug is still there, but it's just masked, because the way the code is structured is it calls the ECU first, and then only if the ECU fails, then it emits whatever the BFI was, the bogon. But the way the ECU is implemented, both the old ECU and the new one, even with the old ECU, it was still, ECU would never completely fail. The ECU would always give you some output when you want output from it. And so the path, the execution path for the bogon to be emitted was essentially skipped, never executes, as a result of the ECU being applied. So they just masked the bug. So now the bug has been fixed, that bogon has been excised. So now, in the absence of the ECU, Osmo BTS TRX will indicate BFI conditions in the same way how Osmo BTS Sysmo and every other model. It's the common layer in L1 SAP that indicates BFI either by intentional gap in RTP stream or zero length payload as configured by VTY. So now I should say, next step is to just get rid of the ECU. So here is my proposal. Okay, so before we get to the proposal, the other thing, I put the slide in there just to emphasize how bad the current situation is. So the current situation is totally inconsistent. Not only is it inconsistent between Osmo BTS TRX and other versions, but also even within Osmo BTS TRX, it'll be inconsistent from moment to moment, because you still have that check in L1 SAP. In L1 SAP, in the path of RTP output, when it has received the uplink output from the BTS model and is preparing, getting ready to send the RTP packet output, it does a check for the link quality. And if the link quality is too low, if it's below a threshold, then it will unconditionally say, okay, this is a BFI. I don't care what the BTS model said, this is a BFI. And under that condition, it will either do a gap in RTP stream or zero length payload per VTY. It will not send out the output of the ECU. So basically, it's, I mean, if someone thinks that having ECU and a BTS uplink is a good idea, at least it should logically be after this check, not before. So you're always emitting continuous unbroken ECU output, right? But here you're applying ECU and then taking the output of the ECU and sometimes suppressing it based on link quality. That's just inconsistent. So, so now we get to proposed solution. So my preferred solution is called an ECU-ectomy. So simply remove it. So the patch is already there. If the community agrees that yes, let's do it, all I gotta do is push it to Garrett. So, but if that approach is not acceptable to communities, we like having the ECU and the uplink, it's a good thing, we don't want to give it up. If that's the community consensus opinion, it's just more work, but we can do it if that's what we have to. So the alternative would be to move the ECU from the TRX model to the common layer, put it after the L1 SAP check, not before, and make it a VTY option. So again, when we get to the discussion phase of this talk, maybe we can decide what we want to do as a community. So that's the ECU problem. All right, so now we get to the GAPK. That's another interesting topic here. Yes, I'm gonna need a little bit more juice, but my understanding is that a lot of Osmocom developers use GAPK in their testing workflows. Mm, So you can see both network side and mobile side. And this line right here is kind of my summary of it. It's broken, but I'm not smart enough to fix it. So let me describe how is it broken and why I'm not smart enough to fix it. So the broken part is that the architecture of GAPK is incompatible with the out-of-band flags. So if we want to have a correct test scenario, like several slides ago toward the beginning of the presentation, I had a slide where we covered the architecture of the standard speech decoder to where every speech decoder, the entity on the receiving end of a stream of codec frames, always begins with the RxTTX handler and then the actual decoder part. So if we're going to have proper voice testing tool, whether it be on a network RTP side or on the mobile side with RxCon, either way, um, it needs to be correct. It needs to do what a standard, spec compliant speech decoder is supposed to do, including the RxTTX handler. And we have the libraries. The Themyscira libraries are released on the public domain license in its official publication of the government of Themyscira, so not subject to copyright. But previously I was thinking, okay, well, let's just propose some patches to add the Themyscira libraries to GAPK. But then I looked at it deeper as no, it's not so simple, because there's a more fundamental problem, not just the lack of libraries, but the lack of out-of-band flags. So all of these RxTTX handlers, both the one that I wrote from scratch for libgsmfrp, for FR1, as well as the ones from ETSI, built into the main body of the decoder for half rate and enhanced full rate, all of these are RxTTX handlers. They all absolutely require out-of-band flags. So there is the out-of-band BFI flag, of course. For HR1, you also have the out-of-band UFI, the unreliable frame. Then you have the TAF, the time alignment flag, also out of band. And in the case of half rate, you would also need the SID classification to be out of band because it can't be reconstructed in band. So you have all of these out-of-band flags, and the architecture of GAPK basically tries to do an anything-to-anything converter. There is just no room for those out-of-band flags anywhere in that architecture. And you can even see from the current code, like, GAPK already supports using for half rate. Half rate is a really good example, because in the case of half rate, GAPK does actually use the official library, well, not library, it's a liberified version from ETSI for half rate. And that official ETSI decoder, of course, has all of those required out-of-band flags. And if you look at what GAPK does when it interfaces to that reference decoder from ETSI, you can see that when you feed things to the ETSI decoder, the out-of-band flags are set to 0. When they take the output from ETSI, they discard out-of-band flags. So throughout the architecture, like in the internal guts of GAPK, you have this canonical format. So first they convert everything to canonical format, then they convert from the canonical format to the target format, possibly run the decoder. I mean, it's all great, the idea, I'm sure, was to do anything to anything conversion. Any combination of input and output will always work. I mean, it's a very laudable design goal, very ambitious. But the bad side is you lose the out-of-band flags. And now so this is how GAPK is broken. Now when I say when I'm not smart enough to fix it, well, that's basically it. Is I'm not smart enough to figure out a way to add these out-of-band flags to GAPK while preserving this whole architecture without rewriting the whole thing from scratch differently. And even if I did have to rewrite from scratch, I wouldn't be able to do it as good, as ambitious. In other words, the whole anything to anything conversion, I don't know how to do it. Whether it by patching JPK as it exists or by writing a new from scratch implementation, either way, I would not know how to create a super ambitious, super generic anything to anything converter that also preserves the out of band flags and correctly passes them to the RxDTX handler. I'm just not smart enough to do that. So here I have a little bit of an alternative proposal. So if I'm not smart enough to implement what I just said, if there's somebody else in the community who is smart enough and wants to do it, great, go for it, please. But if there is nobody else who can do it either, or if there are people who can do it but they don't have the time allocation because that their priorities are higher, etc., what if we can implement a narrower scope tool? Because having a generic anything to anything converter is great. But in terms of actual use cases, do we really need anything to anything? And this is where I'll be in a discussion phase. This is going to be my question to the community. What do people actually need? What are real, actual use cases? Not hypothetical, but the ones that you actually use on a somewhat daily basis for codec testing, voice testing. And if your actual real life scenarios, use cases, are a little bit narrower than a full scale anything to anything converter, maybe we could implement a narrower scope, more specialized tool that handles these actual use cases correctly with the proper RxDTX handler, making use of Themyscira libraries. So that's kind of my proposal here. And that brings us to the end. That is the final slide with the 4 questions. So the 4 questions that are listed on this slide, this is the summary of the questions that are outstanding to the community. So I guess we can discuss some of them on the recording, or we can stop the recording. That's, I'm not sure how much we should discuss on the recording versus how much needs to be off recording. What do you think? So where is everybody? Did I just scare people away with my extensive talking? Oh yeah, Harold has audio problems. Okay, gotcha. All right. Okay. All right. So basically, here's a question. Question from the chat. Thank you, Mychaela, for this presentation. In your experience, is EFR1 still used, or is EFR the standard GSM codec for all phones right now? Well, actually, the answer is neither. The actual answer is okay. Let's break down the question into 2 parts. There's the phone part and there's the network part. As far as what the phones implement, I never test with modern phones. I don't touch like modern Androids, iPhones. I avoid those like the plague. The most modern phone I've tested with is a Nokia C300. That's the model used by my dear life partner. It is a GSM only phone, 2G only, but it is a very late model GSM phone. I think it's from 2010, maybe 2011, but I think 2010. And it definitely implements R99. It implements the USIM interface to the SIM and all this, lots of newer stuff. And as far as the codec support, it's same as every other GSM phone I've seen. Every GSM phone I laid my hands on supports all the codecs. They support FR1, HR1, EFR, AMR. They support everything. And when they send the bearer capability information element to the network, the bearer capability information element always says AMR preferred, then second choice EFR, then third choice FR1, and HR1 last, typically. And of course, the networks typically ignore. Okay, so that was the phone side. What about the network side? In my experience, every GSM network ignores the order of preference indicated by the MS. So the MS in a bearer capabilities information element can indicate what is the order of preference, but the network always has its own order of preference. So it considers the bearer capabilities of the MS only as like a yes or no checklist. So in my experience, the networks always prefer AMR. So if the phone supports AMR, doesn't matter if it's preferred or non-preferred, as long as AMR is included somewhere in the bearer capability presented by the phone, then the network will choose AMR. That's my experience. Now, in order to test what happens otherwise, you have to have a modified MS. You have to have a GSM MS, which you have modified to transmit a non-standard bearer capabilities information element with codecs artificially restricted, which I just very recently implemented in FreeCalypso, and I've been doing some testing with it. So my testing here in the US on okay. All right, so the question, in case of old phones that don't support AMR, C139. Okay, C139 does support AMR. The Motorola C139 does fully support AMR with both the original Motorola firmware and standard unhacked FreeCalypso. So C139 is not a good example. If you want an example of a phone that truly does not support AMR, in the case of Calypso, you have to go really far back to G-sample board. But outside of Calypso, you have phones like Nokia 5190. That's 5190 is the PCS band model, the European equivalent to B5110 and 6110. Those, as far as I know, at least the PCS band models, those do not support AMR, but they do support EFR. And you can also simulate the situation. So even if you have a newer FreeCalypso MS, like 739 or whatever, which physically does support AMR, if you can construct a better capability information element to where you lie to the network and you say to the network, no, I don't support AMR. So that's how you can test experimentally. And I have done these experiments here in the US on the network of operator 310-60, T-Mobile USA, about to be shut down. And their network behaves like this. If there is AMR, they always choose AMR. If there is no AMR support, but EFR is supported, then the network selects EFR. And if the mobile supports neither AMR nor EFR, then the network selects FR1. So this is the decision logic implemented by the network of T-Mobile USA. I could never get it to do HR1, by the way. Could never ever do it. Now, of course, the problem with this network is about to be shut down. They already set the execution date for April of 2024. So in response to this humanitarian crisis, I've been looking into Mexico, which is a neighboring country, and I'm very lucky that the place where I live is literally 1 hour away from the international border by car. So now, of course, my difficulty is I still haven't learned Spanish yet. Something on my to-do list, but you know how it goes. Right now, I'm kind of limited in going there by the language barrier, and I have to rely on some of my friends down there. But I'm trying to explore the Mexican GSM network, see how that one behaves in this regard. There's actually a chance, it's still uncertain, there's a chance I might be going back there later this week, maybe, not set in stone yet. And so I just recently got a new SIM card from Mexican Telcel, their operator, and I was very pleased to see that the GSM 11.11 application is still there. So, and what's so interesting, it was actually May 31st. May 31st, I was back in Tijuana. I was there with my friends. They took me to the Telcel store, like a real mainstream retail store. I walk into the Telcel store and I work, yeah. Harald is making a very, very good point. Yeah, we should. Okay. In defense, I was having this discussion because when I was raising the real points, I was not getting any response. So So let's focus on the open questions that are on the slide right here. We can cover the others later.
So regarding the last point in your list of open questions, JAPK specifically, so as the name suggests, that's the pocket knife. It's not a proper tool, let's say, for coding, for transcoding between different codecs and formats. It's like a hacky solution to quickly test something. And you mentioned in the slide that actively used. I wouldn't say it's actively used within the Osmocom community. It's more like, I don't know, I don't know. I personally don't use it too often, and despite I was the one integrating it into Osmocom BB, into the mobile application, I never used it for testing really too much. It's a lot easier to just set up a real network and test between two phones, two real phones, if you want to listen the audio quality and so on and so on. It's not convenient and not handy, but yeah, it's better. So I wouldn't invest too much man hours into improving JAPK unless you want to make it perfect, unless you're seeking for perfection. So that's my point.
Well, okay, so basically my response to that, as far as improving GAPK, I'm not able to do so. So even if I wanted to, I just don't know how. I said there's a fundamental architectural flaw in there which I don't know how to fix. So my proposal was not so much about the improving GAPK, is more of implementing a replacement for it. So I already have partial replacements for my own use cases. If you look at the GSM codec lib package, the Mychaela wireless GSM codec libraries and utilities package, there's the libraries portion of the package and there's the utilities portion of the package. And if you look at the utilities portion of the package, almost every one of those utilities are my real actual use cases. And also I have another little repository called RTP-debug utils, or RTP-debug tools, I don't remember exactly how it's named, but I have some additional utilities, that analyze PCAP files and extract RTP streams from them. And again, all of those programs there, these are for my real actual use cases. And some of them could be construed as potentially being replacements for GAPK workflows. But obviously my use cases are probably going to be different from other developers. And so my proposal to the community was that if some other people may have a specific use case, like say if you, Vadim, or somebody else uses GAPK in some very particular scenario, very particular workflow, like say as an RTP source, RTP sink, whatever your scenario may be, then I could implement a replacement tool that handles just that one use case, like a use case specific tool that addresses that scenario. That's what my proposal was.
Can you guys hear me again?
Yes.
Oh, that's excellent. Yeah, so I think also GAPK is very rarely used. It was originally developed by Sylvain in the time when we were trying to play with all the different formats, especially the ones implemented in the Calypso and so on. And to convert stuff, but mostly I think in the context of proof of concept and not in the concept otherwise. So, and in terms of using it for development, I guess, yeah, I've used it maybe 5 times in the last 10 years or so. I mean, of course, I'm not representative, but yeah, I'm not aware of any heavy usage of it.
Okay. Okay, well, so, like I said, the offer is open-ended. It can stand. So it looks like from what I'm hearing, is there is not an active demand for a JPK-style use case. But at least, with this presentation, hopefully I made everybody aware of what the problems are. So next time somebody does use it and they get poor quality, well, at least maybe they'll have a better idea as to why. And even when somebody has a specific workflow and they would like a replacement tool that actually works correctly, I'd be happy to implement one.
Yeah. what did I want to say? Yeah, I mean, there are other problems with GAPK. I mean, for example, I don't even recall. I tried to do something with AMR in it, and there's all kinds of constraints with its current model. So there's not really. I think it's the assumption that every codec has a fixed size, but AMR obviously doesn't. So yeah.
Yeah, and I was looking at its recent commit history, and I saw that just very recently, within the past few months, somebody merged a patch that was just hair-raising. How did this possibly get through review? Where it tries to handle BFIs in band and not out of band, and has a BOGO seed frame that's not even close to a valid seed. How in the world of course that kind of raises goes along with what Niels posted on the mailing list just like the night before, how typically in code review people pay a lot of attention to style and quality issues, but fundamental functionality and logic can sometimes go, what, they merged what? So yeah, that's definitely the case with GAPK. There was a recent patch that turns BOGO BFIs into BOGO SIDs.
Yeah, so maybe let's look at the summary of open questions. And so first of all, also, I wanted to say it before, but my audio was acting up. So also thanks again for your presentation and for all your research. It's definitely been one of the rare occasions that I've been able to learn something from a presentation on GSM. So yeah, definitely I never looked into some of those details that you managed to uncover, like these rules for the TRFO and so on. So regarding the questions, HR version 1 codec, well, I'm not sure how many users there are. I think there might be some usage in Rhizomatica, but I'm not sure. Maybe something to ask them. If with phones that don't do AMR half rate, but yeah, I'm not sure. But in general, I think there are no complaints. And yes, of course, there's problems with SID frames and with DTX, but I guess nobody cares about it. So I think it's fine as it is at the moment, at least from my point of view. And if somebody has a problem, they can bring it up.
Yeah. The reason why I was wondering is, yeah, it just seems like so strange. Why would anyone possibly care about HRV1? But also when I saw how just prior to me joining with all these efforts, there was this very active work being done on HR1 when it comes to the two different formats, the TS101, I forget what I think it was the bug number 5688 or something, this issue with the Typhon format versus the RFC 590 format, and you had one of your active Osmocom team members thinking, okay, well, if Osmocom is allocating the time of one of their paid engineers to work on HR1 codec, somebody's using HR1. What? So that was kind of my source of confusion here.
Yeah, I mean, Osmocom supports HR1, so in general, yes, but yeah, as I said, I'm not aware of anyone having particular complaints, and so I guess unless you use DTX, there's not a problem with using.
Yeah. So there was a question here. In Osmocom Themyscira's experience, is HR1 actually usable in terms of audio quality? My answer is not tested yet. I have the curiosity of a cat, and as such, I would like to find out just out of feline curiosity, but no current experience yet.
I think in general it's okay. The problem with HR1 is that you cannot really use it with double transcoding. I mean, it just completely breaks it. So that given the point that most early networks in GSM would always do double transcoding, HR1 was sort of a strange, like, yes, it improved the capacity, but then it only really worked for mobile to LAN calls. And when you had mobile to mobile calls and still the old architecture with G711 and 2 transcoders in series, basically the quality was no longer.
Okay, but I have to correct you there. In that ancient architecture with transcoders, they also had TFO. So I thought, for reasons of HR1 and for other reasons, everybody realized double transcoding was such a bad problem to where I thought that all mainstream commercial actually deployed TRAUs implemented TFO. Or are you saying, am I wrong in it? Are you saying that the TFO was an on-paper spec that was never actually implemented in the TRAUs? Is that what you're saying?
I don't know, and I don't think so. But I think timeline-wise, HR1 is much older than TFO, I think.
Oh, yeah, because I thought they were approximately contemporary. I thought that TFO was being rolled out at about the same time, which of course ties into my other question, how I want to play with a TRAU. I want to actually experience TFO. I want to play with this thing. So, yeah.
Yeah, I don't have a TRAU, so and I don't know anyone who has, so it's unfortunately nothing I can help with. Maybe just quickly feedback to the other topics on the slide here. So the additional, like the TWTS001, I don't mind having some other format, but what I don't like, I quickly looked at the patch as it is at the moment, is that it basically uses the same RTP payload types and it only the size is used to differentiate. So I think ideally, like for a proper solution, I would rather prefer that we actually like during the whatever IPA, CRCX or whatever, some kind of ABIS signaling, the BSC actually tells the BTS and that then we use a different payload type or something like that. So it's very clear which format is used and we don't have to rely on implicit factors such as packet length. That would be my thought on this.
I see what you're saying. Yeah. Okay. This is actually a valid point, and I see your logic in this. In that case, we'll address it after my second proposed presentation, because another topic I would like to present on, probably it could be 2 months from now, 3 months from now, whenever, would be my alternative to SDP on the gateway side. So far in the Osmocom community, it looks like there have been 2 models. There's one model where people use only the internal MNCC within Osmo MSC, and the network operates self-contained. And the other usage model is the Osmo SIP connector, where everything is converted to SDP, and that's how interface to outside the world is done. I have implemented a real production quality working, I use it every day, interface from an Osmocom network to the outside world, to G.711 PSTN, and it is done without Osmo SIP connector. I have my own software, which, I'll be more than happy to discuss how it can be merged into Osmocom mainstream, that connects to Osmo MSC via MNCC socket. And so how the whole architecture is done without using SDP. So, and of course, so basically that one is the reason why it's relevant to answer to Harold's question, can you please stay on topic, is so because you just mentioned having a negotiation through the ABIS to all these protocols.
No negotiation. Just the BSC tells the BTS which payload format is used for a voice call. That's it.
Okay.
is not related to codec negotiation. And regarding the SDP, I really don't want to go there, because then basically, we will never stop getting through any of the topics. So at least I said, from my point of view, in general, I don't mind additional formats, and of course, it's great if we have something that can represent the full feature set of the respective out-of-band information. But let's do it a bit more proper in terms of the choice of which format. That would be my request, and the details we can still iron out if that would be fine with you.
Okay.
Regarding the uplink ECU, well, the background to this is that there is a base station manufacturer who shall be unnamed, who is a customer of Osmocom, and they explicitly requested this, and it solved a problem for them. Now, I agree, it might have been what you described with the bogus 0 bit frames and so on. But for Osmocom, unless we can get this manufacturer to retest with a version, current version that doesn't do those bogus frames, and with the ECU disabled, and have them approve it, we won't be able to disable it completely. And given how the timelines are, and given that it works for them, I think it will take quite some time. So we can request it, but I wouldn't expect any response anytime quick. So it can easily take a couple of months until we get some feedback on that.
Okay, so basically, if for whatever reason they're not interested, if that feedback loop can never be closed, or if they're never satisfied for whatever reason, what is the alternative? I mean, we are currently inconsistent. So, would they object to moving the ECU from the TRX into the common layer and making it optional?
No, that would be not a problem. That we can always do. I'm just saying the complete removal might cause some potentially some regression, so we cannot remove it unless there is some confirmation from them. So that's all.
Yeah. I guess from my point of view, from just wanting it gone, just having a VTY option to turn it on and off would be great. But it would just seem really strange to have a VTY option that turns the ECU on and off when it's actually just TRX model specific, and furthermore inconsistent, happening before the quality check and L1 SAP. It just seems so weird.
Yeah, as Vadim says, let's move it and introduce the VTI option. Those are all non-critical as long as the default with an empty config file or a non-specified config file remains the old behavior for Osmo BTS TRX. Then we have backwards compatibility.
So basically, for default, we'll probably handle it the same way how we handled the HR1 format, where the default is model specific.
Yeah, we could do that. That would work. Yeah.
Because otherwise, if you were to make it default across all models, we'll suddenly be adding the ECU to the Sysmo models.
Yes. Yeah, you're correct. Yeah, model-specific default looks like a good strategy for bug compatibility to backwards bug compatibility, whatever you want to call it.
Yeah.